David Kirtley begins by laying the groundwork for understanding the fundamental differences between nuclear fusion and nuclear fission. Nuclear fusion is the process powering the stars and the universe by fusing light atomic nuclei such as hydrogen isotopes into heavier elements like helium. This mass-to-energy conversion releases tremendous energy, governed by Einstein's famous equation E=mc². Fusion uses abundant materials, primarily isotopes of hydrogen found widely throughout the universe and on Earth, such as deuterium, which exists in seawater, making fusion a potential energy source with virtually limitless fuel. In contrast, nuclear fission splits heavy elements like uranium and plutonium, releasing energy through chain reactions driven by neutron bombardment. While fission provides current nuclear power, Kirtley highlights that the fuel, heavy isotopes mined from the Earth, is finite and problematic due to radioactive waste and risks such as meltdown. Fusion, with its clean fuel and inherent safety features, offers a revolutionary alternative. Fusion reactors can simply turn off without catastrophic failure since they do not sustain chain reactions. This conceptual foundation sets the tone for the podcast's exploration of fusion's technical and societal potential. Delving deeper, Kirtley explains how fusion reactions overcome the natural electromagnetic repulsion between positively charged atomic nuclei. To fuse, nuclei must be heated to extreme temperatures, on the order of 100 million degrees Celsius, providing the kinetic energy for the nuclei to collide despite repelling each other. At extremely close distances, the strong nuclear force takes over, binding the nuclei and releasing energy in the process. This delicate balance between repulsive electromagnetic forces and the strong nuclear force encapsulates one of nature's most profound mechanisms. A key insight is Kirtley's elucidation of why fusion requires intense heat and pressure, far beyond what occurs on Earth naturally, and why the Sun accomplishes these conditions through gravitational confinement due to its massive size. Human-made fusion reactors must replicate this on a small scale using electromagnetic forces, which presents unprecedented technical challenges. Kirtley's discussion underscores that while fission is comparatively easier to sustain at room temperature, fusion demands mastery over extreme physical conditions, positioning fusion as a pinnacle of modern physics and engineering. Kirtley emphasizes the abundance of fusion fuel in stark contrast to fission fuel. Whereas uranium and plutonium used in fission reactors stem from rare mining operations and complex enrichment processes, fusion fuel primarily consists of hydrogen isotopes, which are virtually everywhere, especially in water. He highlights industrially relevant fuels such as deuterium and the rarer helium-3, noting that deuterium alone could supply humanity's current energy needs for millions to a billion years if harnessed for fusion power. The implications of such fuel availability are vast. Kirtley envisions a future where energy scarcity is replaced by energy abundance, dramatically altering civilization's prospects. The fuel's distribution implies that no single country or group can monopolize it, potentially reducing geopolitical tensions tied to energy resources. Fusion's fuel universality and environmental compatibility hint at an energy revolution with transformative societal consequences. A critical theme of the conversation is the inherent safety of fusion power plants compared to fission reactors. Kirtley stresses that fusion cannot sustain self-perpetuating chain reactions, unlike fission, where nuclear reactions can run away if not properly controlled. Fusion systems contain only seconds' worth of fuel at any moment, making uncontrolled reactions physically impossible. Even catastrophic physical events, such as a meteor impact on a fusion plant, would not lead to widespread danger or radioactivity release that necessitates population evacuation. He deflates common misconceptions about fission safety, pointing out that modern fission plants are highly engineered to be safe and operate with multiple passive safety features. Kirtley attributes past nuclear accidents more to human error, regulatory failures, and systemic issues than to fundamental flaws in reactor design. Still, fusion's design promises an additional safeguard due to its physics. If the fuel supply is interrupted, the reaction simply stops, providing intuitive and reliable fail-safe mechanisms crucial for public confidence and regulatory approval. Kirtley offers a nuanced explanation of the relationship between fusion, fission, and nuclear weapons, dispelling myths that fusion reactors could be weaponized. He clarifies that fusion power plants cannot be used to manufacture nuclear weapons materials, unlike fission reactors, which rely on fissile materials such as uranium and plutonium that have direct weapons applications. The so-called hydrogen bomb, or H-bomb, although involving fusion, fundamentally depends on an initial fission reaction to trigger the fusion component. Attempts to build all fusion weapons have failed due to physical limitations of current understanding. Remarkably, engagement with non-proliferation experts reveals that fusion development is encouraged by the global security community. These experts anticipate that commercial fusion power could diminish demand for enriched uranium, reducing risks associated with uranium enrichment proliferation. The hope is that fusion's clean fuel and safe profile may decouple energy from geopolitical and military conflicts, fundamentally reshaping international relations in favor of peaceful energy generation. The podcast details the various approaches to achieving fusion, highlighting the stellarator, tokamak inertial confinement, and Helion's own pulsed magneto-inertial fusion approach. The tokamak and stellarator are magnetic confinement devices using donut-shaped coils to create magnetic fields that trap hot plasmas for extended periods. While tokamaks are more common, stellarators offer elegant mathematical solutions but have historically been more difficult to engineer. These devices aim to sustain fusion continuously, maximizing confinement time. In contrast, Helion's method, based on pulsed magneto-inertial fusion and the field-reversed configuration, FRC, is a linear design that compresses plasma rapidly in pulses, combining magnetic and inertial confinement advantages. This approach utilizes rapid magnetic field reversals to self-organize plasma into a closed configuration, stabilized by spinning plasma analogous to a spinning top. The FRC's natural pulsing allows direct electricity generation and easier scalability, making it uniquely suited for modular, efficient fusion power plants. This contrasts with tokamak reactors, which rely on intermediate heat-to-steam conversion cycles. Achieving fusion requires not only creating the right temperature and density, but also maintaining plasma stability. Kirtley explains the notion of plasma beta, the ratio of plasma pressure to magnetic field pressure, which is close to 1 in FRCs, indicating that plasma pressure matches magnetic confinement pressure. High beta plasmas, while promising for energy density, are naturally unstable. Through careful design and rapid ion spin rates, Kirtley and his team have learned to stabilize the FRC plasma configuration well beyond theoretical expectations. Achieving and controlling 100 million degree temperatures is the pinnacle technical hurdle. Kirtley points out that temperature at these scales represents particle velocity rather than thermal sensation. Ions move millions of miles per hour, making mechanical containment impossible. Controlling the plasma on microsecond scales requires cutting-edge electronics and fiber optic networks, managing tens of thousands of switches in perfect harmony. Thanks to modern semiconductor technology and numerical simulation combined with iterative physical prototyping, the team can pulse, compress, and sustain fusion conditions while extracting energy efficiently. One of Helion's groundbreaking advantages is the direct conversion of fusion energy into electricity, bypassing the traditional steam turbine cycle that dominates fission plants and large-scale power generation. In most fusion concepts, neutrons generated from deuterium-tritium reactions escape in heat water to drive turbines, limiting efficiency to about 30 to 35%. Helion's pulsed magnetic fusion reactor generates charged particles that induce electrical currents directly in their magnetic coils, allowing for theoretical electricity generation efficiencies upwards of 80%. This direct conversion drastically reduces complexity, size, and cost, while increasing overall energy efficiency, which is critical for commercial viability. Furthermore, energy recovery mechanisms enable reclaiming about 95% of the energy initially put into the system, something vital for economic operation. This capability also supports the use of advanced fusion fuels like deuterium helium-3, which produce more charged particles and fewer neutrons, enhancing reactor stewardship and lifetime. Kirtley passionately emphasizes a builder-first philosophy. Rather than waiting years for large, expensive experimental machines, his team pursues rapid, iterative prototyping, building and improving fusion machines on timescales of months to a few years. Helion has constructed multiple generations of fusion prototypes, improving temperature, confinement, and scaling each time. This fast feedback loop accelerates discovery and problem solving. This approach extends to using commercial off-the-shelf components whenever possible, including repurposed hardware sourced from eBay and vertically integrating manufacturing processes. By maintaining on-site component production lines and adopting modular designs with hundreds of smaller coils instead of one massive magnet, Helion reduces lead times and costs dramatically. This scrappy, agile culture empowers the team of engineers, scientists, and technicians to innovate fluidly across disciplines, bridging physics, electronics, manufacturing, and business without sacrificing safety or quality. Looking forward, Helion has ambitious goals, including delivering the first fusion-generated electricity to the grid by 2028 in partnership with Microsoft. This landmark will power real-world facilities with commercial fusion power and set the stage for broader deployment. Kirtley envisions scaling production to an industrial gigafactory level, where fusion plants could be manufactured and deployed rapidly worldwide, particularly supporting energy-intensive infrastructures like data centers. Kirtley also discusses integration challenges with existing power grids and emerging opportunities. Notably, fusion's ability to generate direct DC power aligns well with modern data centers that consume vast amounts of electricity for AI computation. This could allow sites to bypass traditional AC power limitations and boost efficiency. More broadly, widespread fusion adoption could significantly reduce carbon emissions, stabilize energy prices, and redefine geopolitics by removing fossil fuels and uranium supply dependencies, ushering a new era of sustainable energy abundance.